welcome you to the third session of the Fundamentals of Catalysis Symposium today. We have a keynote presentation from Professor Andrew Gellman of Carnegie Mellon University. So without further ado, Andy, if you would.
All right, thank you. We were joking earlier, it was not without further ado, but for somebody who didn't deserve any introduction. All right, so I'm going to tell you a wee bit about a project that's been ongoing in my laboratory for a period of about 5 years. As I've said a couple other times, it's one of those things that's a work in progress. A lot of work, a little bit of progress. But this problem, ultimately, at least from the point of view of catalysis, is one in which we're going to try to understand alloy catalysis across composition space. And so what I'm going to do is first describe the problem that we're motivated by, and that is studying copper-palladium alloys and their application in hydrogen purification. But that's just an example of one of the problems that one could study with the tools that we've invented or developed over the last few years. And so the idea here is to try to study hydrogen reactions on copper-palladium alloys across the complete composition space. And in order to do that, we use a sample substrate or sample library, if you like, that's referred to as a composition spread alloy film. And I will illustrate those to you, but the basic idea is sort of illustrated nicely by that picked graph there, which shows the idea of an alloy with 3 components, and if you can imagine, all possible compositions located in one place. I'll then go ahead and describe for you how we do high-throughput measurements of catalytic reactivity spatially mapped across that composition spread. And then, as a target for sort of the area to end up, show you how we can use this to actually do an experimental correlation of a reaction barrier against the electronic structure as represented by the d-band position in these alloys. So, just to put the problem in perspective, many of the talks that we've heard here, and I'm going to assume in other rooms around the building, have focused on alloys, catalysts that are multi-component materials. 2 components is simple, 3 components isn't so simple, 4 components and higher it gets really complicated. The bottom line, though, is if you're going to think about reactivity in alloys, reactivity or selectivity become functions of the composition. And the composition is at least one continuous variable where x goes from 0 to 1, or it could be 2 or 3 or 4 continuous variables, and you're trying to understand the rate and selectivity of a catalyst across a continuous multidimensional parameter space, which is a difficult thing to do experimentally. It's no easier to do it computationally. Now, of course, the way to think about this is that underlying rate and selectivity is a mechanism that occurs on a surface. And underlying the mechanism is the potential energy surface, the energies of the stable and the transition state intermediates between reactants and products. And of course, the potential energy surface, if you like, or those energetics, become functions of these continuous variables that describe catalyst composition. And of course, the potential energy surface gives you the microkinetic model, if you like, or the barriers, forward and backward, of the elementary steps that describe the mechanism, and ultimately are used to predict rate and selectivity. And if you're an aficionado of some of these concepts, such as the degree of rate control, you can then begin to think about the degree of rate control, which dictates rate and selectivity, also as functions of these continuous variables in a multidimensional space. Okay, now the problem that we're going to use just to illustrate what we're working on is this one of hydrogen purification using these copper-palladium alloy membranes. And the basic idea is that you have a gas stream, it has hydrogen in it and some other components. You want to separate out the hydrogen, and the way you do it is with a membrane that will absorb and dissociate the hydrogen, transport the hydrogen across the membrane, it recombines, and you end up with a purified hydrogen stream here and all the other junk going that way. Okay. The point simply here is to illustrate that on these copper-palladium membranes, you have some pretty interesting surface chemistry that dictates some parts of their performance. So certainly the ability to dissociate hydrogen matters. Things like contamination of the surface matter. There are quite a few interesting surface phenomena that dictate the performance of these copper-palladium alloy membranes. But from the point of view of this presentation, the interesting part is that you can put virtually any amount of copper you want into these things. And the point is, how is that going to influence the surface chemistry? Okay, so we're going to focus in this work on the simplest possible catalytic reaction of value only for this particular problem. That may not be true, but HD exchange, right? H2 plus D2 going to HD serves as a measure of the kinetics for hydrogen adsorption and desorption. And you can run the reaction in steady state. You get a very simple steady state expression for the rate of reaction, and a model for the flow rate out of the HD product here as a function of the two relevant rate constants, the adsorption rate constant, the desorption rate constant, and a few other things such as pressure and flow rates. Now, of course, these things are reversible, so you have to take that into account, but that's not particularly difficult to do. So I'm going to begin by showing you some measurements that we made of the kinetics of HD exchange over a few discrete copper-palladium alloy samples. So these were copper-palladium alloy samples that we took as foils. They're not supported catalysts or anything like that. Simply foils that have been diced up. So the area is 19 square centimeters. That's it exactly, at least as measured with a ruler before cutting it up. And we take D2, H2, flow them over that, and measure the HD yield coming out at the end. And this is the case for palladium. It's a measurement of the HD flow rate out. Here we have temperature, and you can see that as you increase the temperature from 300 to about 500 Kelvin, you see an increase in the HD yield. This data is very nice. This little divot right here is caused by the fact that the palladium converts from a beta hydride to an alpha hydride phase at that temperature. You can see that at flow rates of 9 and 9 milliliters per minute, you get the divot right there. At 4 and 4 milliliters per minute, the net flow rate out, of course, is lower, but the divot is at the same place. If I dilute the 4.5 by 4.5 flow rate with argon so that the pressure of hydrogen is lower, this divot shifts by a few degrees, but that's exactly what's known to happen with these palladium alloys. The fits here, the solid lines, are in fact the fits of that steady state expression using two rate constants to this data across this temperature span. If you go to copper, similar sort of thing, except that the temperature range is much, much higher, right? Not 300 to 500, it's 500 to 900 Kelvin. We measured this over a variety of different copper-palladium and palladium alloys. It's fairly straightforward. This is palladium. There's copper at much higher temperatures. Turns out that palladium is not the most active catalyst for this. If you begin to dilute it with copper, it becomes even more active. What's really interesting here is if you look at the two different phases, the FCC and BCC phase of this copper 53, palladium 47, they actually have vastly different reaction kinetics. But the point is that we've measured these over these discrete composition samples, used these data to fit kinetic parameters. And this is a simple parity plot. So it's the model predicted HD flow rate as opposed or drawn against the experimentally measured flow rates. And of course, the parity line, if all the data fell along the parity line, the model would be perfect. So we will stipulate that the model is not perfect at doing this, but certainly good enough. Okay, now this took quite a long time for some poor guy. It's a couple of nice papers and a nice thesis, but not the way to study HD exchange across all possible alloys. So we can, by the way, we can get the energetics for hydrogen adsorption barriers and desorption barriers out of these kinetic measurements, and we'll use them later. Okay, so now to the big problem. The big problem is that of studying these processes across a continuous parameter space. And in this case, the classic method, the method that we just used, was to take binary alloys, make a bunch of discrete samples, characterize each, measure the kinetics on each, and it took a long time. If it was a ternary alloy, it would take much, much longer time, probably time squared, roughly. Now, the way to get around this is instead of making many discrete samples, to make a sample that has a continuous distribution of all compositions, in this case from pure A to pure B. Or if it was a ternary alloy, to make a sample that might look like this, where you have all A, you have A, B, C, and all possible ternary alloy compositions in the same place. And that's the kind of thing that we're going to do. And then the challenge experimentally becomes to measure the properties spatially, so that you can map out the characteristics or the properties at different compositions across these particular samples. So these samples are known as composition spread alloy films. So we grow them as very thin films on a substrate, just for clarity and truth in advertising. The first paper is written in 1965. I was entering 5th grade at the time. So it took a while before I actually dug this paper out of the literature and found it. But these ideas are well known. They go back a long way. We, in my laboratory, have developed some tools for making these. Actually, it's done by a fairly simple and straightforward process. The apparatus for doing it isn't quite so simple and straightforward, but we developed a tool that will grow these alloys with up to 4 different components, with gradients going in all different directions and whatever, almost whatever you want. And the measure here is an example using copper. So the substrate is about a 14 by 14 millimeter piece of molybdenum. We deposit copper. Over here there's no copper. On the lower right edge it's a film that's of thickness that's constant. And between the two you see a linear gradient in the copper deposition. So when the whole thing is put together and working properly, you can imagine this 14 by 14 millimeter substrate. Sources for A, B, and C, whatever those happen to be. And if you think about the deposition from B, the way this device works is that there's a flux from B which is constant. It drops linearly, and then it goes to 0 here. If you have 3 of these fluxes, sort of all opposing one another, you get a fairly complicated kind of flux field. But it turns out that at the end of the day, on your substrate, you end up with this pattern. So you can, a region that is pure A, one that's pure B, one that's pure C, 3 regions that contain the binaries and all possible compositions of those binaries, and in the center a triangle of material that contains all possible compositions of a ternary alloy. This is an example. This happens to be, again, 14 by 14 millimeter. It's copper plate, gold palladium. If you can see, this color really is gold, that really is copperish, and this really is palladium-ish, whatever that means. It's a lot easier if you have the thing in your hand than trying to take a photograph. But I hope you'll see that it's there. And if you couldn't see it, we can measure the composition. So these are measurements of copper, palladium, and gold on that substrate, measured using just EDAX. This is complicated. I can never even look at it without going cross-eyed. But if you take the data points as measured and plot them on a ternary alloy space, you can see that we cover ternary alloy space virtually completely. Actually, in that case, I won't even go virtual. It is complete. Okay, so that's the substrate. That's the template or the library of materials that we're using to do these experiments. The basic idea here is that you can make these composition spreads, and then if you have the tools available, or you build the tools to allow you to characterize them, you can do things, for example, such as SEM to look at the morphology. You can do EDAX to look at the bulk composition. We do something called electron backscatter diffraction, which maps out the local crystal structure here. We can do X-ray photoemission to look at the near surface composition, helium ion scattering to look at the top surface composition, UV photoemission, which allows us to look at the electronic structure, and again, spatially resolve all of those characterization tools across the substrate. And then, once you've done all that work, measure whatever functional property happens to be of interest. And so in this room, the functional property is going to be catalysis, catalytic reaction. But it could be other things. It could be corrosion rates, it could be hardness, it could be friction, it could be a bazillion other things that you might be interested in. Okay, so let me give you some examples. So this is now just a binary spread, and that's all I'm going to talk about because it's just simply this copper-palladium system. This is a copper-palladium spread that goes from about 5% to 95% palladium. the phase diagram for copper palladium is shown in the bottom. So it goes from 570 to 1170 Kelvin, from 30 to 90% palladium. And it's a fairly interesting, more interesting than average phase diagram, at least for a binary system, because copper is FCC, palladium is FCC, and yet, believe it or not, somewhere around 50%, there is a phase which is actually a BCC phase. Technically, it's something called a B2 phase, but it has a BCC structure. If you go to high enough temperatures, of course, that fades off, and then around here, you have purely the FCC region. So we made a film, copper palladium, annealed it to about 800 Kelvin, and then we can do an experiment which is called electron backscatter diffraction to look at the phases that we've developed in our film. So these are electron backscatter micrographs. So this is a 12 by 12 micrograph. Every point on here in this micrograph, and you can sort of see some of the points, are indexed by the electron backscatter diffraction to be either the FCC or the BCC fraction. The FCC's fractions or points are in red, the BCC points are in green, and you can see that we follow the phase diagram almost exactly. So it's FCC, FCC, mixed phase, BCC, 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 mixed phase, and then FCC. Okay? And in fact, if you look, it's 2% variation in composition. It leads you from something that's pure, not pure, but almost purely FCC to almost purely BCC. So the phase transition occurs, or the two-phase region, if you like, occurs over a very narrow range, and we can map it out exactly as predicted by the published or existing phase diagram. You can actually do more than that. You can actually look at each grain and figure out how it's oriented with this backscatter diffraction. So these are maps of not the crystal structure, but the orientation of the grains. This one here, you can see lots of grains, right? Here you can see some grains. This one is copper 95%, so it's mostly FCC, but everything's blue, or almost blue. And what that means is that the grains are all oriented around the 111 pole. So this is a copper palladium alloy in the FCC phase, which is almost copper palladium 111 single crystal, almost. Here, when you have the FCC region, but with low copper composition, you can actually see that there are two different types of grains. Some of the grains, or most of the grains, are oriented around 111, but there are a few grains oriented around 001. So it's a copper palladium 111 single crystal with a few 100 single crystals embedded in it. When you're in the BCC region, well, it's everything. Okay? They're just randomly oriented grains at the surface. That's all that you can tell. Okay, so now another property of these alloys that is probably relevant to catalysis, or the catalysis we're going to look at, is segregation. Of course, in all alloys, one of the two components is going to segregate to the surface. These composition spread alloy films are ideal substrates for trying to study segregation, because you have all compositions present at once. So in our hands, we can do X-ray photoemission, so X-ray in, photoelectron out, and use that to measure the composition in the near surface region, call it the top nanometer. You can do helium ion scattering, so it's helium in, bounces off, and you measure the energy loss, and that tells you exactly the composition of the very atomic topmost layer, because the helium won't penetrate the alloy at all. And then, of course, we can also do UV photoemission, so it's a UV photon in, photoelectron out, measure the energy of the photoelectrons, and you can look at the valence band structure of these alloys, but as a function of composition. Okay, so here's some data. This is segregation in the alloy film that I showed you. I'm only going to show you the top layer segregation here with helium ion scattering. And what I'm showing is the copper concentration as a function of the bulk concentration. This is the one-to-one line, which you would get for an ideal alloy, which was non-segregating. And the reality is that it segregates, not surprisingly, and copper segregates to the surface. You can see that. You can measure that as a function of alloy temperature, so 300, 500, 700, 900. So what's really interesting is that the segregation of copper increases and then goes back down once you exceed about 700 Kelvin. And that's something, by the way, that we've observed on a standard foil of copper palladium alloys. It's no different from that. But the interesting thing is that out of this segregation behavior, because you can measure it across temperature, you can get the heat of segregation. So segregation is just an equilibrium property, provided temperature is high enough to allow you to reach equilibrium. But you have copper to palladium in the top layer, copper to palladium in the bulk, related by an equilibrium constant. And because we can measure this equilibrium across various temperatures, we can get delta H out of this free energy. And the heat of segregation, as you go from 0 copper to 100% copper, goes about -5 kilojoule per mole towards 0, which is where it should be when you get the heat of segregation for copper out of pure copper is 0. Okay, so now let me sort of, having given you the characterization of this film, hone in on the catalytic reactivity of the surfaces. So what I'm going to try to do here is do what we see in many computational descriptions of catalysis, but do it experimentally. So the idea is to correlate reactivity with electronic structure. So you've seen many of these. So this is a measure of dissociative, not a measure, actually it's a computed barrier to dissociative absorption energies of hydrogen and oxygen on platinum alloys that contain a variety of components. And it's plotted against the position of the D band. And the correlations that one gets from DFT very often show linear correlations between barriers and D band positions. And the question is whether or not we can see that experimentally. So I took this particular one out of one of my colleagues' past work, because I feel free to take his work and show it anyway. So how are we going to do this? So we need to measure catalysis. So in addition to making tools for making composition spread alloy films, we designed and built a multi-channel high-throughput reactor. So it's glass. It's shown here in somebody's fingers, not mine. But you can see at the end there's a region that's about 1 centimeter by 1 centimeter. And in that centimeter by centimeter there are 100 reactors, each one isolated from the other, each with its own feed and product stream. And we can flow gases into each one of these reactors and out of them, and they come out the back end. There's a lot of capillary gas handlings or gas lines out here. You can't really see them, but it's a mess. And of course, we have to couple that with this composition spread alloy film. But you take this, you plop it down on top, and it isolates 100 different regions in a 10 by 10 array, and you can flow H2D2 into each of them, and then measure the HD out. And then spatially, because it's spatially resolving, measure HD exchange rates at all possible compositions across that composition spread. So we use a mass spectrometer to measure rates. A very useful tool for this particular thing and for many other things that we want to do. This is just an example. So these are measurements now. It's a palladium, gold, copper. HD exchange or HD flow rate out, mapped across 100 different channels on this composition spread. This particular composition spread didn't cover the whole of ternary alloy space because it was made with a slightly different tool, but you get the picture. You can measure quite well the HD exchange rate or flow rate out as a function of alloy composition across a continuous span of alloy composition space. Okay. So here we have, to begin with, then the UV photoemission from the copper palladium alloys. Okay, it's a mess. Okay, but it's measured across spectrum measured from 100 different compositions across that one alloy film. It's pretty clear that as you go from pure copper or almost pure copper to almost pure palladium, that you have a shift in the valence density towards the Fermi edge. Okay, the Fermi edge being right about there. So we have done our best to map the position of the Fermi, the D-band level, energy level, or the D-band center. It's copper and it's palladium, so the D-band is almost full. Not quite, but almost. So we take these and use them as just raw measures of valence band density, and use those then to plot the D-band position as a function of copper concentration in the alloy. Okay, it goes from about just below 15% copper here to almost 95% copper. Okay, Now the next thing then is to measure HD exchange kinetics. So it's H2D2 kinetics measured in that reactor from about 300 to 600 Kelvin, so a reasonably wide temperature range. Here we're looking at the H2 conversion as a function of temperature. These are too small to see, but this happens to be 13% palladium, so almost no palladium and almost nothing happening. You can increase the amount of palladium in there. Now it's 19% for those of you in the back, and there's next to almost nothing happening. At 26% palladium, now there's something happening as you get to high temperatures to convert H2D2 to HD. At 33%, now you can see the conversion to HD. At 55%, we're starting to approach full conversion. And at about 63%, you're getting to what in this corresponds to 100% conversion. Now, if you remember, going back to the beginning of my presentation, I said that palladium itself is actually not the most active catalyst for HD exchange. And we showed that using these palladium foils in standard flow reactor conditions. Well, you see the same thing here. So when you go from 63% palladium to 73%, well, let's say that's the same. But when you go from 73 to 82%, it goes down. And 82 to 88% goes down even further, and 92% even further. So in fact, we're seeing here phenomenologically exactly the same behavior as a function of alloy composition as done with those alloy foils that we used in a flow reactor. The difference being that, although I haven't shown you all 100, there are now 100 of these. We can take 100 of those curves, we can use the same model used before to extract kinetic parameters, so the absorption and the desorption rate constants and the activation barriers for dissociative absorption and desorption. That is now shown here. So here we have the energies, desorption energy, adsorption energy. Palladium concentration going from about 5 to something like 70%. You can see the measurements made, say for the adsorption case, using those foils earlier in the flow reactor. And you can see the desorption energies here. And so what we measure kinetically for the adsorption energies is an adsorption barrier of something like 0.15 eV. But as you go to higher and higher copper concentrations or lower and lower palladium concentrations, the barrier to adsorption goes up to something on the order of about 0.4 eV. And done across now many compositions. Almost a continuous spread. Okay, now the question is, what does this look like when we take this data and correlate it? Well, let me go back. Remember, we have this data. So we have D-band center versus composition. Over here, we have barrier versus composition. Hence, we can now try to correlate the adsorption barrier for hydrogen on these alloy films with the position of the D-band. So what do you see? So over a pretty wide range of compositions, from say 30 to 85% copper, it's pretty linear, as one might predict. But it's not that simple. There's actually, from 85 to 95, it's pretty linear also. It's just they don't have the same slope. So something's going on. Now, do I know what it is? No. These linear correlations can work, but they're not as, I think, not as simple as you might like them to be. And that's probably because there are things that are going on in the real system here that one doesn't typically account for in trying to do simulations of these things. The obvious example, and it may not be the reason, but an obvious case here, is that when you get to high copper concentrations in these alloys, copper segregation could get to the point that it virtually eliminates any of the palladium at the surface. And so the real surface, if it's effectively 100% copper, won't dissociate H2, which is effectively what's occurring up in this region here. And therefore, changes in the D-band of the bulk material that we're measuring aren't representative of the real electronic characteristics of the copper, of the surface, which may now be predominantly copper. Okay, so I have gone relatively quickly, but that's fine. We'll have some time for questions if there are any. But I've introduced a few thoughts here. One is the use of these composition spread alloy films. to study alloy catalysis across composition space. I would like to make the point that although this is definitely a high throughput methodology, the point here is not to use a high throughput methodology simply to optimize a catalyst for highest activity or selectivity. It's to take data across the entire composition space and use it to try to understand something about the fundamental mechanism or the energetics of the reaction and the energetics of elementary steps as they're influenced by composition across composition space. I've illustrated this high throughput reactor and then tried to draw this correlation between what we can measure for an absorption energy for hydrogen and the D-band center. And I think that's likely to be the first sort of experimental correlation of those two parameters, at least with the number of points on the plot that we have here. Okay, so I'm going to quit right there, or close to there. Let me acknowledge the people who did this work, quite a few people over quite a few years. Casey O'Brien. Jim Miller is actually going to be talking on Thursday and perhaps giving some other applications of these tools, or maybe even some more details about how we do some of the things that we do. So I would happily go to his talk if I were here on Thursday afternoon. And then Topeka, Peter, and Gamze, who've done a lot of this work. The funding has come from a variety of sources over a number of years, from DOE through the NETL, the Moore Foundation, believe it or not, that is Moore of Moore's Law, and the NSF. And before I quit, I think I'm obligated to invite you to Pittsburgh. The next NAM meeting will be in Pittsburgh in 2 years. It's easy to get there. You just go down to the river, get in a boat, and paddle upstream. Do not go downstream. If you paddle upstream, you will ultimately arrive right here. So you will be retracing the steps taken by Lewis and Clark. Now, once you get to here, you have to deviate, because Lewis and Clark left from somewhere over here. Convention Center is just over here. So when you get here, turn left, go about a mile, and then just pull up to the Convention Center. If you start on Friday or maybe Saturday morning, you should be there by June, 2020. And in my estimation, it might be faster than going by United, so may well be worthwhile. All right. I will try to answer questions.
We have time for a few questions. Andy's left us lots of time for questions. So,
thank you for the very nice talk. So you have perhaps an opportunity also to look at the effect of grain size on these processes by controlling the substrate temperature. I wondered if you tried that and whether or not that messes up the composition control, that you get more segregation. Have you considered?
So now are you asking the grain size effect on catalytic activity?
Yeah,
we haven't tried that. The grains here are fairly big in the sense of hundreds of nanometers to micron-sized grains, and so I would not necessarily expect.
What temperature is your substrate?
Well, we can do whatever. In this case, these were annealed typically always to 800 Kelvin, which is not super high. One of the things I would say that we can do here that we have yet to do, but will, is that if we make the initial film thin enough, then when you anneal the substrate, the film will de-wet. And so in fact, what we can do, and if we do it in such a way that there's, from left to right, if you like, there's a gradient in thickness, you can anneal these films to de-wet to create nanoparticles then which have a gradient in size. And so in 2 dimensions, we could make films that have a gradient in size going one way and a gradient in composition orthogonal to it and do fun things there. Yeah.
Fascinating talk. You showed that the rate was first increasing with palladium content and then decreasing. And then your activation energy is linear in this regime. So can you please explain why the rate is decreasing?
Yeah, so I think that the way it works is this, right? So there's 2 things going on. There's adsorption and desorption in parallel simultaneously. What's happening as you start to put copper into the film is that you decrease the desorption energy. So in these films, certainly when you have a high palladium content, under the conditions in which this is being run, the surface is close to saturated in hydrogen. And so, although you have to absorb hydrogen, so the absorption barrier matters, the desorption barrier in that regime is also mattering. If you lower the desorption barrier, which you do by adding copper, then you can increase the rate up to some point, but not infinitely. That's what I believe to be occurring.
Thank you.
Great talk, Andy. So I wanted to ask you, do you have any insights to share with us about the atomic scale geometry or topology of copper and palladium size that would give you some relevance, I guess, for the exchange reaction itself?
So you're sort of asking an ensemble?
Yeah. Is it monomers, dimers? Do you have any information on that?
From this, I would say no. I mean, not from what I've shown you or done here. There's a paper that John Kitchen and Charlie Sykes wrote about 3-4 years ago, where they certainly looked at palladium on copper in situations where it was fairly dilute, and were able to say something about the ensemble size there, or give some ideas, because they were able to image the distribution of palladium sites in copper film, and then look at the ability of that film to absorb hydrogen. So I think there is some knowledge, but not from this.
There's a question
I have two questions. First, of course, from the UPS data, you showed that the band is shifting, and also in backscatter electron diffraction, you showed the phase change from FCC to PCC to FCC. I wonder whether you were able to measure the lattice parameter change and correlate it with the composition for the FCC structure. That's the first question. Second, in your last graph where you showed this two slope, two linear slopes, on the one which goes up, there is a region where you go from FCC to PCC, and V2 structure, and back to FCC, if I understood correctly, but there's it doesn't seem to affect the barrier, so I wonder whether this is because the D band is very localized and there's no effect of the crystal structure on the activity.
Yes. Okay, so the first question was related to the lattice parameter. The lattice parameter certainly changes. People measured it in these kinds of alloys. With electron backscatter diffraction, there are people who are really, really good at this claim that you might be able to measure lattice parameters with electron backscatter, and we'll probably try it with a colleague of mine who claims to be really, really good at this. But it's on the hairy edge of what people can do with the electron backscatter tool. So it's worth trying, but I'm not sure what we'll get out of it. So the point about the phase transition, or the issue of going from FCC to PCC to FCC, I think there are two things. So in a clean alloy, you can certainly see that happen. You can't really see anything in those UPS spectra that shows any discontinuity in the valence band. But what's really amazing is if you look at the core level shifts, so you go to copper, you use XPS, you look at the core level shifts, now I'm going to have to draw in there, right? So you've got the core level energy versus composition, and the core level in copper is shifting up, 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 and then there's a discontinuity, up, 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 another discontinuity down, and it goes to the FCC. So the core level, for whatever reason, is extremely sensitive to, it's a combination of lattice parameter and phase transition. The valence levels don't seem to show the same thing, and it may be some degree of delocalization that matters. I don't know. The only other thing I would say with respect to the measurements of kinetics are that, there's a lot of hydrogen there. It's quite possible that hydrogen that it will be on the surface and may also be in the near surface region is also going to influence that phase transition. So do we know under the exchange conditions whether we have FCC or BCC phase in that particular region? No, not really. So it's complicated, and there's some parts of that so I can address some parts of what you're asking, but not the whole thing.
I think to keep ourselves on
Absolutely.
time, we're going to have to cut off the question period. Join me in thanking